be different, like we do if instead of being a conducting sphere, right? Like solid insulator, how would that change this? It doesn't change anything outside of case A. The parts B and C are exactly the same. But for part A, instead of doing what we did, we would have to think about what's the charge enclosed in the Gaussian sphere that I drew in this whatever color this is. So we'd have what? We'd have Q enclosed divided by epsilon naught is equal to, 4 pi r squared times E. But the Q enclosed, we would do 4/3 pi little r cubed divided by 4/3 pi big R cubed times Q. That would give me my Q enclosed. I divide by epsilon naught. Did I ever move my camera? Oh man. Oh, seriously? Oh, I'm the worst. Well, sorry people at home. But there was something written there that I just erased. Oh, this is the bad thing is I'm tired this time of day. I'm gonna make some mistakes like this. So let's see here. So all that we had before I moved the camera, this was just a conducting sphere, and we had 0 up here because the charge enclosed is 0 if it's a conducting sphere. So
I'm
dang it.
Confused by how you got that ratio.
So the amount of charge inside the sphere is the ratio of the volume of the.
Okay.
So I'm taking the ratio of the volumes to get the percentage of volume that's inside. That's all.
Yeah.
I took the ratio of the areas in the other problem.
That was the volume.
So, but we could do something like total volume, like charge divided by total volume is equal to charge enclosed divided by enclosed volume.
Yeah.
And if we set up that equality, that would give us.
The exact same ratio.
Right. Yeah. And so these cancel, and you're just going to get E is equal to, let's see here, Q QR divided by 4 pi epsilon naught R cubed. Which is exactly the formula we derived in class this week for that problem, because inside the solid sphere, that's the thing, is you can work inside out, right? What happens in the interior is completely unaffected by what is outside with these kind of spherically symmetric problems.
Would that ratio work even if the small r was bigger than the bigger r?
Whoa, I don't know what you mean by that.
Like, if...
How could the small r be bigger than the... I mean, the context here is the small r is inside r.
But like, if we just assume that that didn't have to be the case, and the small r was bigger than the radius of the...
Well, if the small r is bigger than the radius of where the charge is,
on the outside,
then you've got all the charge. So that puts us to case B.
Okay. Okay.
Like there's no ratio to think about because it's you got the whole charge.
Okay. Okay. Yeah. I get that.
I mean, we could work a problem with variable charge density if that would be interesting. I will do it in class next week probably, but. Let's see here. So that was problem 41, and I looked at the answers in the back, and we got them. Okay. Here, what time is it?
5:30.
All right, maybe one more example for today then, right? I try to find one where we have to use calculus, maybe. Let's see here. Yeah, let's do 45. So this may help answer some of your, well, maybe it'll help start to show what we have to do when we can't just take ratios and we actually have to, kind of like work out the calculus. So I've deliberately made examples where we can avoid calculus so far, right? I mean, the flux calculus is there, but we're always circumventing it with a symmetry argument, right? You see that? Yeah. So this is problem, yowzers. Problem 22.45. And so here it is. It's an insulating hollow sphere of inner radius A and outer radius B. All right, and within the insulating material, the volume charge density is given by rho is equal to alpha over R, where alpha is a positive constant. All right. So again, we're looking at 2245. All right. So part A. In terms of alpha and A, what is the magnitude of the electric field a distance r from the center of the shell, where A is less than R is less than B? And then part B, it says a point charge Q is placed in the center of the shell. And then I think it asks at R equal to 0. And then in terms of alpha and A, what value must Q have, sign and magnitude, in order for the electric field to be constant in the region A less than R less than B? And then what's the value of this constant field in the region? Whoa. Dude, interesting. All right. Well, here we go. So let me talk about this. Charge density is charge per unit volume, right? So this is dq dv. So in order to figure out, like, if I think about my Gaussian sphere, right? Somewhere in here. What's the big problem if this Gaussian sphere, let me call it radius r, all right? Gaussian sphere radius r. So the question is, what's the charge enclosed there, right? So this is an insulating sphere, so like this is a hole in the middle. All right. In part B of the problem, they put a charge at the center of this thing. But to start with, it's just a hole, and so you've got charge smeared out in this region. How do you calculate how much charge that is? You're told the density is given by alpha over the radius, where r is the spherical radius. So what you want to do is you want to, like an onion, think about spherical shells, right, of distance r, and like the thickness of the shell will be dr. See, so like the volume of such a shell is 4 pi r squared, yeah, times dr. And so the infinitesimal charge on such a shell is exactly alpha over r times 4 pi r squared dr. So the infinitesimal charge on that one spherical shell is apparently 4 pi, all right, so 4 pi alpha r dr. But there's a context here, right? This is for what? A less than or equal to r less than or equal to b. So how do I calculate Q enclosed for my Gaussian sphere? I need to add up the charge on all the little spherical shells, right? Starting at A. That's where it starts, right? All the way out to here. All the way out to here, right? Which is R. So from A to R, I have to integrate 4 pi alpha r dr. And that will give me the charge enclosed.
Wait, the charge enclosed in the entire sphere?
Inside the Gaussian sphere of radius big R.
Okay, yeah. Okay.
We're actually not told how much charge is enclosed in the entire shell, but we'll be able to figure that out pretty easily here in a second. Once we do this integral, we can just plug in big R equal to B, and then we'll know the net charge. So like this integral, we can do it, yeah? So you got yourself a 2 pi alpha r squared, evaluate that thing from A to R. We've got ourselves a 2 pi alpha big R squared minus A squared. So there's your charge enclosed. So finally not a ratio, right? Like this, we actually had to do some calculus for this one. But nevertheless, this problem still enjoys the wonderful spherical symmetry of our most of the problems we work, yeah? And so we can still apply Gauss's law to that Gaussian sphere of radius r, big R, and that will give us, over here, we got ourselves a Q enclosed divided by epsilon naught equals to 4 pi. In this case, I'm using big R squared for the radius of the Gaussian sphere, right? Like that. And so what do we got? We've got the electric field is equal to apparently 2 pi alpha big R squared minus little a squared divided by 4 pi epsilon naught big R squared, right? And of course that's radially outward, right? That's the magnitude. Does that formula make sense? Well, let's think about some things. What happens if we put big R equal to A?
Big R is equal to A, it would be 0.
Does that make sense? If we think about the Gaussian sphere shrinking down here to the inner radius, what's the charge enclosed then? 0. So the electric field 0 at the inside surface. On the other hand, what's the, by the way, so we can also, like you asked me, well, maybe you didn't really ask me, but you made me think about it. What's the Q enclosed for R equals to, big R equals to B? That would be like 2 pi alpha B squared minus A squared, right? So notice that if this is like, we could call this Q total, right? And notice that like the electric field would be Q total divided by 4 pi epsilon naught little r squared for r greater than or equal to B.
For the electric field, you can cancel out the 2 pi and the 4 pi, right? So it's just
Oh, sure.
that over 2 epsilon naught r squared.
Yes, we could simplify that. I wanted to leave it because I want to point out that if you think about the case that the radius big R goes to B, at that point, like past that, any radius larger than or equal to the outer radius of the insulator, it's just going to be like a Coulomb field again. It's going to be the total charge divided by 4 pi epsilon naught, the radius squared. So like once you're outside of where the charge is distributed, for all intents and purposes, it's equivalent to just a single charge in the middle of Q total like that, you know? That's how these work, is like, this is the same as that if we're outside of you know, like B. It's just the Coulomb field again. Now that's not what this book problem does something different for part B and C, I'm just talking. For part B and C, they add a charge little q at the center and ask an interesting question, so we should go back to that. But does this so far make sense? Like this is just part A of the problem. Let me check. Uh-oh. What is this, 22.45? So the book has alpha over 2 epsilon naught times 1 minus a squared over r squared. Is that what you said?
Yeah.
So this is alpha over epsilon naught. Did they put a... They kept the 2. Alpha over 2 epsilon naught. If I do that, then I've got r squared over r squared, which is 1, minus a squared over... well, I'm going to put a little r squared here down there. So like this would be the electric field at r for a less than r less than b. All right. So thank you. Like that's what I needed. That algebra you were talking about is what I needed to do to see the book's answer. Cool. I was interested in another comparison, so I went another way. Okay, but anyway, let me erase the comparison business and go to the next part of the problem, which was kind of interesting and a little bit surprising to me. What's the rest of the problem say? Problem 45. It says, part B, a point charge Q is placed at the center of the hollow space at r equal to 0. In terms of alpha and A, what value must Q have in order for the electric field to be constant in the region A less than R less than B?
Should it be a squared over big R squared down there?
Well, I'm changing. I was changing the little r, the big R to little r here.
Okay.
Is all.
Yeah, okay.
All right, so let me erase my stuff. Okay, so then part B, they say, okay, well, put a charge Q here, right? And then the question for part B was, what Q is needed at r equals 0 to make electric field constant inside the shell. Right, so let's think about it. So we would, if we put Q there, what's the electric field inside the shell then? It would be what? It would be Q, right, over 4 pi epsilon naught times 1 over r squared, right? Plus what? Plus the thing we just calculated. Alpha over 2 epsilon naught, parentheses, 1 minus a squared over r squared. Can I erase the Q enclosed calculation at this point? Oh, okay.
I'm still a little confused on when you got the Q enclosed from the first part.
Oh, go for it. Yeah, okay, so what am I doing there? So the place where there's charge, right, is in here. So like, now, I mean, there's charge outside of there as well, but we're looking at this Gaussian sphere of radius r, where r is between the little radius and the big radius. So I'm trying to calculate the charge there. We're given that the charge per unit volume is alpha over r. So what I did was I took this shape and I divided it up into spherical shells, like an onion with a hole in the middle of it, you know? So like the volume of a spherical shell is 4 pi r squared times dr, right? Because that's the area of it and the thickness is dr. So then I just basically put that up into here and I solve for dq. So dq is alpha over r times dv. Well, this is the dv and that's the rho. So this gives me the amount of charge in that one shell. And if I want to find the total charge enclosed, I have to integrate from where the charge starts, which is at A, all the way out to where it stops, which is R. I mean, sure, there's more charge out here, but we don't care about that because we're looking at the Gaussian sphere of radius R.
And the R can change depending.
Yeah, we need to set up Gauss's law, we need to set it up for like an arbitrary R in the case we're interested in. So like the one R you can't choose, you can't put A here and you can't put B here because then you can't, that just tells you what happens at like the inside case or the outside case. You want to pick an arbitrary radius in the region of interest. So, and then we add up the dq's by integrating. And I'm sure that you don't have a problem on the calculus part of it. No one ever actually has. Students always tell me, I understand how to do the integration. I just don't understand how to set it up. It's like, yes. So like, I honestly, like, I do think there's really nothing, you could teach that kind of mechanical integration to children of a much younger age, right? The setup of integrals, the motivation for writing formulas is much deeper. And that is the part that people get confused on because that's the hard part. So it's good that you're asking questions about it. It really is the hard part. Let me erase though. Can I erase now? So like look at what we're up against. We want to make this constant inside the shell. What should we do? It's kind of a quirky algebra problem. How do you make the shell field constant? Well, you can't have a dependence on over r squared, right? How can we get rid of the r squared dependence? This is a funny question. You want to make the q term cancel the r squared term? Yeah, like, let's see. So let's do the math here. We rearrange a bit, right? So we've got like E shell is q over 4 pi epsilon naught minus alpha a squared over 2 epsilon naught, all of that times 1 over r squared, right? So my point is, let's group together the things with r squared. Let's understand like what we're up against. So this part, that's fine, that's constant, right? We're allowed to have that. But the question is to make the electric field constant. So we must somehow make this 0 to make it constant, right? How do you make the 0? Well, set that coefficient equal to 0. We got it, yeah. So we need q over 4 pi epsilon naught equals to alpha a squared over 2 epsilon naught. So solve for q. We've got q is alpha a squared times 4 pi epsilon naught divided by 2 epsilon naught, which I think we can solve. We can clean that up a bit. The epsilon naughts, they be canceling. And 4 over 2 is 2, so we get what? 2 alpha, got an a squared, anything else? Pi. All right, this is an odd problem. So moment of truth, right? 4.25. Part B, q is equal to 2 pi alpha a squared And the constant value the electric field takes is alpha over 2 epsilon naught, which is what we have, right? So this will make the electric field equal to alpha over 2 epsilon naught in this case. This is a very neat problem. It's a cool problem. I've not seen this problem before, and it's been in front of me the whole, I have had this book forever. This is the book I took, that course I was telling you about, that I took as an undergraduate first, was from this book. This is the book I studied out of. This is a book my wife studied in high school, because she was like a pure math, she was interested in physics in high school, and some professor told her to study this book there, so she did. But it's a classic. We were using a different book a couple years ago, but I had to harangue Professor Dromby into using this book instead, because the other book has 20 or 30 problems at the end of the chapter. This one has 80. You can get so much more out of working the problems in this book. And so the difference between 80 and 20 or 30 problems is significant, because if you've got 80 problems at the end of a chapter in a physics book, that means you've got the answers to 40 problems. That's enough to understand things from, right? You got 20 problems, 30 problems, you got the answer to 10 problems. Is that enough? Not as much, So anyway, I'll try to make an announcement later with a list of problems that I recommend. It will, of course, include all of the problems we've worked here today. And then I'll try to pick out a couple more, just because I'm trying to recommend 10 problems from each chapter. I try to recommend odd ones so that you guys can,